Hello everyone, welcome to all in this lecture. So in this lecture, I'm going to discuss stress in a bars, right? So we'll discuss what is the stress. Okay, so to understand the stress, you can see in this figure A. So there is a body, and that is in the equilibrium condition by four forces F1, F2, F3, F4. So by these four forces, this body is in equilibrium condition. This force is in equilibrium condition. So now we want to know that in between, what are the internal stresses or internal forces developed. So to get that, what we are doing, we are just cutting this section in two parts. This is the first part, this is the second part. Now, and in the B part, figure of this B part, we have drawn a free body diagram. Free body diagram. So you can see there is a F1, F2, and see we have cut the section from this portion. So now you can these are the distribution of all the forces, right? And this distribution of forces, whatever is mentioned here, so we have uh, shown in this third figure by the resultant, right? So where Fr is the resultant of distribution forces, resultant of distribution forces, right? On this section, on this section, cutout section, right? And Mr is the moment of resultant of distribution forces, moment of resultant of distribution forces, right? So what we have done in the first figure, that's body was in equilibrium condition by the four forces. Now we cut the whole body into two parts, 1 and 2, and we have drawn a feedback diagram for the first part. And these are the some distribution of forces shown in the figure by arrow. And the resultant of this distribution of forces we have shown by Fr and Mr naught. Fr is the resultant of distribution forces and Mr naught is the moment of resultant of distribution forces, which is acting on O, where O is the centroid of the section of the cutout section, we can say. Cutout section, right? Now, so now the whole section, suppose the total cross section area of this section is capital A, right? So we are assuming a small segment that is delta A, which is very small, very small section, very small area, we can say, right? And we are assuming that on this delta A, very small area, there is a force acting delta A, that is very small force acting on this a small area delta A, right? So now we can resolve this delta A forces in the perpendicular direction according along the x-axis, along the y-axis, or along the z-axis. In this figure, you can see this is the this is the y-axis, this is the x-axis, and this is the z-axis. So whole this delta F forces, this is a small force which is acting on delta A area, we can resolve in y direction, x direction, or z direction, right? Now you can also see in the figure this delta A, that is, suppose this is the area of delta A, which is in xy plane. One side is x and one side is y. So which is in xy plane, right? This one is the xy plane. So now we have resolved this delta F in z direction. So delta F z, one is along the y, that is delta f z. One is along the x, that is delta f in x direction, right? So now we can say that delta fz will be the normal to delta a, normal to a small area, and this force says delta fx and delta fz will be tangent. So now we can write here delta fz is normal to delta a, and delta fx and delta fy are the tangent to delta a, right? Now delta a is very small, right? So once delta a will approach to 0, so what will happen? Delta a will approach to 0, it means we are finding the stress or force at a point. So once delta a will approach to 0, so the fraction of delta a, delta f and delta a, delta f and delta f to delta a will be a finite limit. So limit will be a finite value when delta a goes to 0. Are you getting my point? When delta a, the small area, approach to 0, we are approaching to 0. So the delta f or delta a, the fraction of this will be a limiting value, the limiting finite value. We can write like this. And this finite value is called a stress. This finite value we call a stress, right? So by the definition, we can write the intensity of internal forces acting on a specific area, that is, in case delta A, are passing through a point is known as stress. On the other hand, we can define the force of resistance per unit area. Force of resistance per unit area offered by a body against deformation is known as stress. Are you getting my point? Okay. So now we are going to calculate along the plane or along the axis, right? So now we are going to calculate a stress along the z-axis, stress along the z-axis. So notation we can write sigma z. So that will come limit delta A goes to 0. What force will come? Delta sigma z in the vertical direction, and when vertical direction in the case in the along the z direction, that is delta fz, force is delta f divided by A. So now this is called when the intensity of force acting along normal to small area or a specific area, that is delta A in this figure, defined as normal stress. For normal stress, generally we denoted by sigma. This is called sigma, right? And for the direction, we are just writing sigma z. So when the normal stress in z direction, sigma z, when the stress along the x-axis, we will write sigma x. When the stress along the y-axis, that is sigma y, right? So we can denote by normal by sigma j. So the intensity of force acting Normal to delta A or a specific area or a specific plane is defined as normal stress. Now, normal stress, what are the type of normal stress? When suppose this is a prismatic bar, this is a rod, and where two or equal and opposite forces are acting on this pushing force are acting. So in this case, what will happen? The length of bar will decrease. Decrease the length of bar. So whatever the stress will develop in this case, that stress will come as we call as compressive stress. Compressive stress. So whatever stress will develop in this section anywhere in this rod, that will be compressive stress. Similarly, when the two pulling forces acting equal and opposite, P forces, you can see these forces are equal and opposite. In this case, that length of rod will increase the length of one. So whatever the stress will develop in this case, we can call a tensile stress. Tensile stress. We can call it tensile stress. Notation will be sigma only. There is a sign convention in this case when the stresses are tensile stress. So we take the sign convention is positive. When stresses are in compressive in nature, we take the sign convention is negative. Right? So normal stress are two types, compression and tensile. Now shear stress. We have seen in the last slide that delta Fz, we have seen in the last slide, delta Fz was normal to delta A, but delta Fx and delta Fz are tangent to delta A, right? Now, so the intensity of force acting tangent to a specific area, a specific plane, delta A, is called shear stress. It's called shear stress. So what we can write, what is the stress when delta is goes to 0, approach to 0. So we will define limit delta A goes to 0. Now, what are the forces which is acting on tangential? So always we have to find the direction or plane. What plane we are writing? So we are writing on zx, tau zx. So what force will come here? Delta F z or x or y, what? So once you will write z, but z is normal to delta A on delta A, right? So this will be normal. We have to take the tangent, acting tangent to a specific area. So tangent is, so we have taken the x, so you can write delta fx divided by delta f. Similarly, we can write tau z y. On this plane, so limit delta A goes to 0, delta f, what? Z we can write because z is a normal to this delta A. So we'll write delta y. So these are the shear stresses. Shear stresses means you have to take the what are the forces acting tangentially on that area. Tangentially on that area and divide by the what are the area. This is the tangent. tangential force we can write. This is also tangential force. Okay, now you can see in the figure. So again, we have cut the section. So on this area, what are the area? What you can write? This area. So you can write, see, whatever the normal will come, that is sigma y. This is the normal. A straight in what direction? Along in x, y direction. Here, tau yz. Tau yz means the plane is yz. So whatever the shear stress, so we can write like this: shear stress on yz plane. YZ plane, along the YZ plane on what area? Delta A. Similarly, we can write for this shear stress along YX plane. Suppose, so we have to find the plane, what are the plane and what are the area. So here in this case, delta A that we have considered delta A. This is delta A and delta wall is along the Y, along the X and perpendicular normal to this plane, XY plane, that is Z. So in this case, where delta Fz was normal to delta A and delta F and delta X was the tangent to on delta A, right? So whatever the when we will divide the area from the normal force, it will give us the normal stress. When we'll divide the area from the tangential force, it will give us the shear stress. It will give us the shear stress. There are two assumptions on this for this theory. And what are that? First, that materials should be continuous. It means continuous. It means material should be uniformly distributed. Material should be uniformly distributed, right? And second assumption is cohesive. Material are cohesive means it means what? Cohesive means all the portion of the material should be connected to each other. There is no break. There is no gap. There is no separation between the material. So all the portion of the material should be connected. So the portion of material should be connected, right? Average normal stress, axially loaded bar. So that I will discuss here. So now we have seen whatever we have calculated the shear stress when delta A goes to 0. So the fraction of delta F to the delta A is give us the limiting finite value that is called stress. So now we will take the, now see in the figure, average normal stress. So suppose this is a circular bar, which is length L. Okay, this is a circular bar of length L. Okay, and there is a force acting. I'm writing a pulling force, that is P. Force P is acting now. And this area is capital A, total area, total cross section area. Now, when I'm cutting a section from this, I'm drawing a figure, everybody down with this section. So what will happen? Here a pulling force E, and now I'm going to, so this will be resistance. This will be the resistance. So now from the definition, we know that here is the, suppose this area, P is the normal to this area. So we can write sigma will be limit delta equals to 0, delta. We can write P divided by delta A. So now when we are assuming that there is a uniformly distribution of stress, uniformly distribution stress. Uniformly distribution of a stress means for all a small segment or a small area of this total A will be having equal resistance force. Will be equal resistance force. So now we are assuming that delta F is the resistance force by delta A, so that we can write sigma into delta A. Means there is a uniformly distribution of stress, means sigma is everywhere throughout the total area. So we can write for this small area, resistance force will be delta F. Now we want to know, or we want to calculate total resistance force. So we can do the integration by changing delta F into dF. So we can change delta F equal to sigma delta A. Taking integration both the side, what we can get? F equal to A totally, right? Or we can write stress equal to A. Here, this sigma we can also call normal stress, or in particular in this case, we can also call tensile stress. Because why? Because you can see in this figure there is a two equal and opposite pulling forces are acting on this body, on this bar. So we can call it tensile stress. That will be F by A, right? Where sigma is a normal stress or a stress induced normally inside the inside this body, inside this length, or we can say on the cross section of this length. So this area is this one. So and F is the resistance, total resistance on this cross section, and A is the total force. Now I'm saying that total resistance is calculated, that is F. So from the equilibrium condition, we can write P is equal to F, right? From the equilibrium condition. So finally, we can write sigma is equal to F by A is equal to E by A. Right? So whenever you want to stress, and this is how it came. So this is average normal stress. Average normal stress, and there is assumption that this stress is uniformly distributed throughout the section, right? This is the average normal stress. Whenever you will see if the stresses is not uniformly distributed, so this formula will not apply there. It will not apply. Whenever if the distribution of a stress is not uniform, then in that case this formula will not valid. It will valid when the stress distribution is uniformly throughout the section, right? First numerical we have a rod of length 1 centimeter, 150 centimeter, and dia 2 centimeter, subjected to a axial pull 20 kilonewton. So now we can draw a figure like this. This pulling force is 20 kilonewton. Determine normal stress of the rod. We have to calculate normal stress of rod. What is the formula? E is equal to divide by A. A is the cross section area. So what will the cross section area here? Diameter is given. This is circular. So pi by 4 into d square. Pi by 4 into d square. Right? D is given 2 centimeter. E is given. So directly we can apply the formula, that is 20 kilonewton. So I'm writing 10 to the power 3, that is Newton, and divide by pi by 4 into d square, 2 square centimeter square. So it will come Newton per centimeter square. What is coming? Let's calculate. So it is coming 6. It's coming here 6366.197 centimeter per Newton per centimeter square. Right? Second question we have, a bar has a constant width is given, that is 35 mm, and a thickness 10 mm, right? So here you can see in this figure, this length is given 35 mm, and cross section is given like this. Cross section is given, that is 10 mm thickness, right? Width is given 10 mm thickness is given, right? So determine the maximum average normal stress in the bar when it's subjected to loading shown in the figure. The question which is mentioned, maximum average normal stress. See, whenever the pulling force or the pushing force are equal throughout the section, so this normal stress will be constant inside the body or throughout the length of bar. But in this case, you can see here, you can see here is 12 kilonewton and here is 22 kilonewton. So first we have to calculate on this section. You can divide the whole in 3 segments like AB, BC and CD, and let's calculate what are the pulling forces or pushing forces are acting on this segment AB, BC and CD. Then we can find out the normal stresses. Then we will see what are the maximum normal stresses, right? First calculate. So first draw the periodic diagram of AB segment. So this is the AB segment. Here, this is the free body diagram. Here, force is acting 12 kilonewton, right? And here is there is action and reaction. So just assume there is a force F. So from the equal condition, this force also will be 12 kilonewton. Now I draw the forces here. It is A and it is B. Now draw a free body diagram from A to some other axis, like some section in between B. So I'm drawing a free body diagram for A to X. This position is X. I'm drawing a free body diagram A to X. This is A. This is position is X. This X position is in between B and C. Here is the B, and somewhere here is the C, right? Pivot diagram I'm drawing. So this is the 12 kilonewton. Just assume some other force F. Now we will see at the B position there is a two external forces are coming. 9 kilonewton, 9 kilonewton. So there is two external forces, 9 kilonewton and other is 9 kilonewton. Now I'm taking the sign convention. Right side is positive. I'm doing this summation of x because this portion A to x is equilibrium condition. So this will be this is equal to 0. So I'm taking minus 12, minus 9 plus F will be 0. So from this equation, F will come 12 plus 9 plus 9, 30. Means is this portion, this F is called 30 kilometers. Now draw the periodic diagram. Right. Now draw the periodic diagram C and some other section like from giving a name like X, right? C to X. So I'm drawing a periodic diagram X and this portion is D, right? X is a point between D to C, in between D and C, right? So here is one force is acting. I'm drawing a free body diagram. So this is 22 kilonewton, and assume some force is acting like this F. From the equilibrium condition, we can write 22 kilonewton. Now we can calculate normal stress for AB section. That will be F by area. Area is constant throughout the cross section area is constant throughout this length, throughout the length of this bar. So we can write 12 divide area, that will be 35 mm into 10 mm, this kilometer. Now sigma normal stress for BC. In BC, what are the pulling force? 30 kilonewton. In BC, what are the pulling force? 30 kilonewton. So F divided by A, 30 kilonewton, divided by area, that is 35 mm into 10 mm. Now calculate the normal stress for the CD. F divided by A, what are the force? 22. See, bottom denominator are same in all the cases. So denominator is 30 kilonewton, that is maximum. So this value will be maximum, and this is the maximum average normal stress. This will be the maximum. This is also normal stress. This is also normal. This is also normal stress. And maximum will be this one. And what value will come? Maximum will be sigma BC, that is 30 kilonewton divided by 35 mm into 10 mm. And this value is coming 87. Sorry, 85.7 Newton per mm. This is in mm, this is mm. You have to, what you have to do? Just multiply with 10 to the power 3, it will become a Newton, and then we can find this one. 85.7 Newton per mm, right? This is the one book I have preferred to make this lecture, Mechanics of Material by R.C. Hewler. Also, you can prefer this book. Thank you. Next lecture, I will discuss strain.